All right, welcome back. We're doing Ted Shifrin 1.4.2. That's chapter 1, section 4, problem 2. This is a two-part problem. So part A is if A is an m by n matrix. This is going to be the notation I use for that. This is just the set of matrices that are m by n. Of course, we're going to assume they're over R. So all elements are real numbers. And we know that for all x that's in Rn, so this is a vector now, vector in Rn, a times x is 0. And that's necessary, right? This has to be an n-dimensional vector because this is an m by n matrix. So for multiplication to work, that has to be an n-dimensional vector. And we're saying that for all x, this product is 0. What we want to show is that then implies that a must have been 0. If every time you multiply this x vector by a, and you get a 0, well then that must mean that a is 0, right? If I'm going through all x's in Rn. The second part is to show that if these are two matrices m by n, and ax equals bx for all x in Rn, that must have meant that the matrices were equal. Okay, so we're going to prove this, and we'll start with the first part. Now for this one, I'm going to use the technique of, I'm going to use contrapositive to prove this. And just so that I do a quick little recap in case you're not quite sure what that is, just remember contrapositive works like this. If you have two statements, P and Q, and we have an association here, P implies Q, that is equivalent to the statement not Q implies not P. If you look at the truth tables on these, you'll see that, depending on the truth values of P and Q, when you evaluate at the truth values of P and Q, they'll show to be equivalent for equivalent values of P and Q, right? So this statement, P implies Q, is the same as the statement not Q implies not P, right? This is sort of denial of the consequent. When you deny the consequent, you have to show that that implies the denial of the antecedent as well. If you can do that, then that's the same as showing P implies Q. Okay, so that's what we're going to do. So here, I'm going to be denying that a is equal to 0. And I'm going to show then that that means that I can get some x so that a times x is not 0. Okay, so we proceed by contrapositive. Let a be different from 0. So this is me denying q, right? My consequent, right? So a is not 0. It's not the 0 matrix. Well, if it's not the 0 matrix, there must be something in it that's not 0. So there exists some I and j. That's kind of a weird bracket. So what this is saying is if you take the ijth element of the matrix A, once again, this is the ijth element of the matrix A. Since A was not 0, I mean, for some I and j, I don't know which, but for some pair here, you're going to get that that element isn't 0. Because if they were all 0, it would have been the 0 matrix. So I can guarantee myself that I can find something like this because I'm assuming it's a non-zero matrix. OK, so we're going to let x here equal to AI transpose, where AI is the ith row of A. So basically, remember, x here is going to be this vector in Rn. And what we're setting ourselves up for is we're saying we want to find, remember, when I deny this, I want to deny this. And what does it mean to deny this? What does it mean to show that this is false or that the negation of this is true? Well, if for all x equals to 0, for all x in Rn, ax equals to 0, negating that would say that, no, I can find an x in Rn so that ax doesn't equal 0. It's not the case that every single one of them is 0. That's, of course, assuming that I'm denying a is equal to 0. Okay? Just to kind of give a little motivation, I'm not going to go too much into it, but this is kind of one of those things where you might ask, well, how did you know to do that? I mean, how did you know to take the ith row of this thing? I mean, where did that come from? And here's where I think if matrix multiplication with vectors, so this is a matrix and this is a vector, if that multiplication still sort of appears to you as kind of like it's nuts and bolts, if it's very mechanical, if you're thinking of it as, Aij, if you're thinking about it in terms of a formula, right, the sum formula, it might be difficult. It might be difficult. You kind of need to step back a second and kind of generalize the idea. And I think he talks about this in the section as well. And the basic intuition here is going to be, okay, well, is there any sense in which I can sort of relate this to something that I can control in terms of setting it equal to a vector of zeros or some sort of vector? And the answer is yes, because you can think of matrix multiplication with vectors as dot products, right? You can kind of think of it as if you have a matrix A, right? When you multiply that matrix by a vector, all you're really doing is taking a bunch of dot products, right? So you take the first row, and it's almost like you're just taking its dot product with the vector, and whatever comes out, that's the first entry, right? Take the second row, dot it with the vector, and that's your second entry. Take the third row, dot it, and so on and so forth. So there's some sense in which this is kind of, you could think of it as a dot product. And dot products are nice because if you recall from either your reading or some of the problems that we've solved, you can kind of control dot products. For example, I can say if x is not 0, x dotted with x is definitely greater than 0, right? Which is going to give me a handle on this equation here because, right, this thing is only equal to 0 if all of its components are equal to 0. But if I can think of its components as a bunch of dot products, well, if I just pick the right thing to multiply by, I'll make it so that I can be sure that when I do that multiplication, I won't get a 0 for that component. I'll get something bigger than 0. You're going to see this is actually going to come up in just a second here. Okay, so that's kind of the intuition. That's kind of where we got the idea for this. Okay, so we're going to take, just to recap, we're going to take the ith row of A and set it equal to x. So now, when I multiply A times x, where remember x is just the ith row of A turned into a vector. So I just transpose it, so now it's acting like a vector, and now I can multiply these, right? Okay, this is going to be, well, A was an m by n matrix, and x was a vector in Rn, so Ax is just an m-dimensional vector. What we can say is, and I'm being quite explicit here when I do this, really don't have to add the 1 because we know since it's an m-dimensional vector, there's only one column on this thing, right? But I'm trying to be explicit here is when I multiply these two things, right? When I look at the ith row, that ith row, when I multiply by x, is just like multiplying the ith row of A dotted with itself, right? So I'm going to say that's x dotted with x. Because remember, x is just the ith row of A. So when I get to the ith row of A and I multiply by x, well, x is just the ith row of A written as a column vector. So when I do the multiplication, it's really just like doing its dot product with itself, this x here with itself, which we know is non-zero because it came from the ith row of A, which we know had a non-zero element, which means it's greater than 0. Thus, Ax does not equal 0 for x equaling Ait, which is an element of Rn. And this is our proof, right? This is showing that when we deny this, we get the negation of that. We can find an x so that this actually doesn't equal 0, right? And which one was it? Just set x equal to the ith row, where that ith row is just a row where we know A has something that's different from 0. Okay? All right. So that's part A. Now, actually, I think we can do part B in the remaining space because it's going to be pretty straightforward. Part B asks us to show that when we have two matrices that are equal on multiplication with the same vector x for all x, that must mean that the two matrices A and B were equal. Okay, so here's what we do. So Ax equals Bx for all x in Rn. Let's subtract by bx, so we get ax minus bx equals 0 for all x in Rn. And remember, this is the 0 vector, because these are going to be spitting out m-dimensional vectors. But now we can pull out that x, we can factor it out, and we get a minus b times x equals 0 for all x in Rn. And I forgot the n here on the previous one. But look, by the first part of this, what are we saying? We're saying that this thing times x equals 0 for all x in Rn, and in our first statement, we know that when that's the case, that must mean that matrix was 0. So a minus b is a matrix. Remember, they subtract component-wise. But it's a matrix such that when I multiply by any vector in Rn, I get a 0 vector that comes out of it. Well, by part A, this means a minus b is equal to 0. Now add b, and a equals b. And the matrices were the same. All right, that's it. Hopefully that was helpful. And all right, I'll see you guys in the next video.